let's solve some previous year gate problems from psychrometry and heat pumps and cycles. So firstly, I am going to take some questions from psychrometry. A sample of moist air at a total pressure of 85 kilopascal, total pressure 85 kilopascal, PT, representation of the total pressure as PT, 85 kilopascal, has a dry bulb temperature of 30 degrees Celsius. The saturation vapor pressure of water at 30 degrees Celsius is 4.24 kilopascal. So this PVS is 4.24 kilopascal at 30 degrees Celsius. Okay. If the air sample has a relative humidity of 65%, the absolute humidity in grams of water vapor per kilogram of dry air. Okay, so I have solved these type of questions in the previous video also. So phi is 0.65, which is equal to PV upon PVS. Okay, PV is the pressure exerted by water vapor and PVS is the saturation vapor pressure of water. So we get PV is equal to 0.65 into PVS, which is 0.65 into 4.24 kilopascal. So that implies PV is equal to this will be 2.756 kilopascal. Okay, so why we have found out this PV? Because absolute humidity is equal to 0.622 PV upon PT minus PV. So put this PV here. PT, that is the total pressure, is 85 kilopascal and PV is 2.756 kilopascal, and you will get omega is equal to, if you put the value, it will be 0.020843. The units will be kilogram of water vapor per kilogram of dry air. Okay, and we have to find the absolute humidity in grams of water vapor per kilogram of dry air. So that implies multiply this by 1000. Omega will be 20.843 grams of water vapor per kilogram of dry air. Same type of question is coming again and again in the exam. Okay, let's see the next question. The next question is a stream of a moist air. The mass flow rate is given, that is 10.1 kilogram per second with humidity ratio. Okay, so omega 1 is 0.01 kilogram of water vapor per kilogram of dry air, mixes with a second stream of superheated water vapor. Okay, so the second stream is superheated water vapor only. Assuming proper and uniform mixing with no condensation, the humidity ratio of the final stream in kilogram per kilogram of dry air. Okay, so we have to find this. Omega is equal to m dot v total upon m dot a total. Okay, this is the humidity ratio of the final stream. Okay, so here stream 1 is coming, here stream 2 is coming, and they are mixing, and this is the stream which is going out after mixing. So let this be m dot 1, which comprises of dry air plus water vapor. So I am writing them as m dot a1 plus m dot v1 for this first stream, and for the second stream m dot 2 is equal to m dot v2 only, because this second stream is superheated water vapor only. Okay, so its value is 0.1 kilogram per second. Okay, so mass flow rate of water vapor in the second stream is 0.1 kilogram per second, and here m dot 1 is 10.1 kilogram per second, which comprises of dry air plus the water vapor. Okay, and the humidity ratio of the first stream is also given. Okay, so if we use this humidity ratio, that is omega 1 is equal to 0.01, which is equal to Humidity ratio is equal to mass flow rate of water vapor upon mass flow rate of air in this first stream. Okay, so use this relation 1 and 2 and find out the quantity of water, I mean the mass flow rate of water vapor and the mass flow rate of dry air in the first stream by using 1 and 2. Okay, so let's solve this. 0.01 m dot v1 upon this will be 10.1 minus m dot v1. Okay, so when you solve this, mass flow rate of water vapor in stream 1 will be equal to 0.1 kilogram per second. Okay, and put the value in this equation 1, you will get that m dot a1 is equal to 10 kilogram per second. Okay, so first stream has the mass flow rate of water vapor as 0.1 kilogram per second. The second stream comprises only of superheated water vapor, so the total mass flow rate entering in this final stream will be 0.1 plus 0.1 kilogram per second, and the total mass flow rate of dry air is 10 kilogram per second. So this is 0.2 upon 10, and this will be 0.02 kilogram of water vapor upon kilogram of dry air. So this is 0.02. So this is the humidity ratio of the final stream. Okay, let's move on to the next question. Next question is, air in a room is at 35 degrees Celsius and 60% relative humidity. So phi is 0.6. This is phi. The pressure in the room is 0.1 megapascal. That is 100 kilopascal. And this pressure is the total pressure that the question is talking about. So PT of the room is 100 kilopascal. Okay. The saturation pressure of water at 35 degrees Celsius is 5.63 kilopascal. So PVS is equal to 5.63 kilopascal. The humidity ratio of the air in gram per kilogram of dry air. Okay, again the same type of question has been repeated. So you see, I mean almost every year the same type of question is getting repeated. So this is very important question. This type of question is very important, where the relative humidity value is given and you have to find the humidity ratio by using some other data. So humidity ratio is equal to 0.622 PV upon PT minus PV. This will be in kilogram of water vapor per kilogram of dry air. Okay, so we have to find this in grams per kilogram of dry air. Be very careful. Okay, and phi is equal to PV upon PVS. So phi 0.6 into PVS is 5.63 kilopascal. That will give me PV is equal to the value will be, I guess, 3.378 kilopascal. Okay, put this value PV here, and PT we know, which is 100 kilopascal. So omega is 0.622. 3.378 upon 100 minus 3.378 kilogram of water vapor per kilogram of dry air. Solve it. This will be 0.02174 kilogram per kilogram of dry air. Okay, this is kilogram of water vapor. Okay, so this is omega, but we have to fill the answer in gram per kilogram of dry air. So multiply this value by 1000 and you will get the humidity ratio or the specific humidity in grams of water vapor per kilogram of dry air. So this is 21.74 grams of water vapor per kilogram of dry air. Okay, so this is our answer, 21.74. So this type of question is getting repeated again and again. I mean, so let's move on to the next question. Okay, the next question is, in a mixture of dry air and water vapor at a total pressure of 750 mm of Hg, okay, the partial pressure of water vapor is 20 mm of Hg. Okay, so the total pressure is 750 mm of Hg, that is rho g h. H is 750 mm. Okay. And the partial pressure of water vapor is 20 mm of Hg. So that implies rho g 20 is the partial pressure of water vapor, that is PV. The humidity ratio of the air in, again in grams of water vapor per kilogram of dry air. Again a very simple question. Omega is equal to 0.622. This is PV upon PT minus PV. Okay. So do not worry about the units that I have written the height in mm here, because they will get cancelled out. So 0.622, any conversions will get cancelled out. So rho g PV is 20. See, they're getting cancelled out. Even if you have written here it in meters, it wouldn't have made any difference. Okay, so 750 minus rho g 20. So this value comes out to be equal to 0.017041 kilogram of water vapor per kilogram of dry air. Okay, and you have to write the answer in grams of water vapor per kilogram of dry air. So that implies multiply again this by 1000, and omega, humidity ratio or specific humidity, the value will be 17.041 grams of water vapor per kilogram of dry air. Okay, that is 17.041. This is our answer for this question. Okay, next question. Okay, so this question is from heat pumps and cycles. So let's read this question first. A heat pump absorbs 10 kilowatt of heat. Okay, let's draw a schematic diagram first. So a heat pump absorbs 10 kilowatt of heat from outside environment at 50 Kelvin while absorbing 15 kilowatt of work. So this work input is 15 kilowatt, and this is the surrounding which is at 50 Kelvin, and it is absorbing 10 kilowatt of heat from the outside. So this is heat pump, and this is our room which is at 300 Kelvin. Okay, so let this be Q1, let this be Q2, the heat which is actually going into the system. So from conservation of energy, Q2 will be equal to Q1 plus W, and Q2, that the heat which is entering into the room, which is equal to 15 plus 10, that is 25 kilowatt. Okay, so this is the heat that is entering in the room. The coefficient of performance of the heat pump is, so coefficient of performance of the heat pump is equal to Q2 by work input, because in heat pump Q2 is our desired effect, but in case of refrigerator Q1 is our desired effect. So here a heat pump is given, so Q2 is our desired effect, and COP is equal to, that implies COP is equal to Q2 upon work input. Q2 is equal to 25 kilowatt that we have found out just now. Work input is 15, so that is 5 by 3, and which is equal to 1.67. So the COP of heat pump is 1.67. Okay, next question. Standard VCRS with a condensing temperature of 35 degrees Celsius and evaporating temperature of minus 10 degrees Celsius develops 15 kilowatt of cooling. Okay, the cooling effect is given, the value is given as 15 kilowatt. The pH diagram is given and the enthalpies is given at various states. If the isentropic efficiency of the compressor is 0.75, the isentropic efficiency of the compressor is also given. The magnitude of compressor in kilowatt is, okay, so let's draw the TS diagram from this pH diagram of the VCRS. This is a vertical straight line, and 1 2 2 dash 3 4. 1 4 is the refrigerating effect, 1 to 2 is isentropic compression, 2 to 3 is the heat rejected in condenser, and 3 to 4 is throttling, that is isenthalpic throttling. Okay. So the isentropic efficiency of the compressor is also given. So extend this constant pressure line above. So due to this isentropic efficiency, the actual work input will be like this. Okay, let me draw it. So this will be the actual it's very difficult to draw here. Yeah, somewhat like this. This will be a curved line, dotted, and this will be the actual work input to the compressor. Let this point be 2 double dash. Okay. So they have asked us to find the magnitude of compressor work. So the magnitude of actual compressor work will actually be equal to m dot h2 double dash minus h1. Not, and it will not be m dot h2 minus h1, because h2 minus h1 is the isentropic compression, whereas 1 to 2 double dash is the actual compression, and they have asked us to find the magnitude of compressor work, actual compressor work. So this is work dot input actual. Okay, so let's see if we have m dot h2 double dash or h1 from this pH diagram. Okay, so with this, from this pH diagram, this point is 1, this is compression, 1 2 is compression, 3 3 4 is throttling. So at 1 the enthalpy is 400 kilojoule per Kelvin. So H1 is 400 kilojoule. Sorry, the enthalpy is 400 kilojoule per kilogram, not Kelvin. So H1 is 400 kilojoule per kilogram, and the enthalpy at the state 2, that is after isentropic compression, H2 is 475 kilojoule per kilogram. 475 kilojoule per kilogram. And H3 is equal to H4 because the throttling is considered to be isenthalpic, and H3 is equal to H4 is 250 kilojoule per kilogram. Okay, so this point. Okay, so we have H1 now, and we don't know H2 dash, and we also don't know m dot. So let's use this value. The isentropic efficiency of the compressor is 0.75. So isentropic efficiency 0.75 is equal to the isentropic work input upon the actual work input. Okay, so 0.75 is equal to this will be isentropic work input is h2 minus h1. It's actually m dot h2 minus h1, and actual work input is m dot h2 double dash minus h1, but this m dot and m dot is will get cancelled out, so that implies 0.75 h2 is 475, h1 is 400, the difference is 75, and h2 dash minus h2 double dash minus 400. So solve it. H2 double dash will be equal to 500 kilojoule per kilogram. Okay, so now we have H2 double dash also. Okay, so we have H1, we have H2 double dash. The next value that we have to find out is m dot, but there is one more data is given in the question, that is it develops 15 kilowatt of cooling. Okay, so the refrigeration capacity is m dot h1 minus h4, and this is equal to 15 kilowatt. So m dot can be found out from this equation. H1 is 400, h4 is 250, and this is 15 kilowatt, and here it is kilojoule per kilogram, so no need to change the kilowatt in watt or kilojoule in joule. So m dot is equal to 0.1 kilogram per second. Okay, so now we have m dot s2 double dash and h1. Put the values in this equation here, and the answer will be 0.1 into h2 double dash minus h1, that is 100. So this will be 10 kilowatt. So the actual work input to the compressor or compressor power, work dot input, so or the compressor power is 10 kilowatt. Okay, thank you.